I see that now we have all joined the course, so I can officially begin. Okay. Good morning and welcome everybody to this Mathematics 2 crash course for IBA. My name is Bianca Ghiță and I will be teaching this course today and tomorrow. We have 8 hours of crash course organized into 2 days. We are going to be meeting from 9 to 1 today as well as tomorrow. And now let me tell you a little bit about our course before we begin. So as I've said, my name is Bianca Ghiță and I am going to be your teacher. Some of you may recognize me from the statistics crash course of last semester for Statistics 2, and other people maybe from Statistics 1 of last year. I've also taught that one last year. I've included here on my screen already some of my contact information in case you have questions or something's unclear. This is my email address. I've also sent you an email this morning at around 8, inviting you into a WhatsApp group chat. In case you didn't get that email, or still haven't checked your email and saw the link, or maybe simply I have inputted your email address wrong, please text me on WhatsApp. This is my personal phone number. I will make sure that you're added to the group. It's not mandatory that you're in the group. However, I will be sharing the PowerPoint presentation, some more study material, and the exercises that we work with today. Some of them I can't include in the slides because their graphical representation is way too complicated to create in a PowerPoint. Therefore, I've done them on some pieces of paper, and I would be more than happy to share them with you because they're really, really well explained. So I think that would be very useful for you to have after the crash course as well. How is our course structured? So I've divided the 5 chapters into 2 days of classes because I believe it is really important for us to first understand the first 3 chapters really, really well. So therefore, we can go into more in-depth into chapters 4 and 5, which is what we're going to do tomorrow. How are we going to work? I'm going to do as many exercises as possible from these 3 chapters today because I know how important they are to be really, really well understood. After each chapter, we're going to take a 5 to 10 minute break according to how tired everybody is. If we're a little bit more tired, we're going to take a little bit of a longer break so everybody can get a chance to get a cup of coffee, some water, and just relax because I would need you to be really fresh all throughout these 4 hours. And lastly, tomorrow, we're going to work chapter 4 and 5, again with exercises, but I have let some special time at the end of the crash course. I think it will be around 2 hours that I have put together only for working past exam papers. So we're going to do together live past exam paper exercises from what I think are the hardest or the hardest to understand parts of the course. And we're also going to see how they're applied in the actual exam paper, because of course that is a different structure from how the book is written, for example. This is my planning and this is what I wish to do with you guys. Now, I want you to be able and to feel free to ask me as many questions as possible via chat, or if you wish to speak up, that's also completely fine. I'm going to try to reply to everything promptly. However, if you see that I'm not replying to something right away, it means that probably I still have an idea or two to connect together so that the final thought makes sense. So if you see that I'm not replying right away, don't worry, I'm not ignoring you. I'm just waiting to be able to explain it fully in just a couple more minutes. Okay, so that was all from me. And speaking of the crash course, now we can officially begin with the presentation of the chapters. So we're going to start with the first chapter, chapter 1, matrices and application. For anybody who has never seen a matrix before, a matrix is a rectangular scheme of numbers, which consists of a number of rows or lines and a number of columns. The graphical representation of the matrix is represented as this picture here on the right. We can see this matrix called A, which is represented by these rectangular parentheses, and it contains all of this information, which are numbers. We will later on find out they're actually coefficients, indicated by some indice. 1, 1, we see 1, 2, 1, n, and so on. The numbers inside the matrix, so these positions A, are called positions, and they are going to be read or recognized depending on first the row on which they belong and then the column from which they belong. For example, if I ask you what is the number on the position 2, 3, that is going to be represented by the coefficient A 2, 3, which is the number situated on the second row, third column. In our matrix, it would be exactly on the right of this indici A22. So it would be the number exactly next to it. This is a matrix, and this is how we read the coefficients inside the matrix. There are three special sorts of matrices that we're going to extensively work with in our course. These are the square matrix, identity, and vector. What is a square matrix? A square matrix is a matrix which contains the same number of rows and columns. So instead of having m rows and n columns like in our official matrix in the original one over here, now we have the same number of rows and columns. Nothing else changes. The indices are the same. Their positions are exactly the same. We read them exactly the same. The only difference is that the number of rows and columns correspond with each other. A special sort of square matrix is the identity matrix, which contains a unit position or a number 1 exactly on the diagonal of the matrix. I've included here the most commonly used identity matrices, although most of them we'll never see it again in our lives. We will mostly work with the identity matrix I2 and I3 because we mostly work with square matrices 2 by 2 and 3 by 3. I4 and I5 we will rarely see. However, if it happens that you stumble upon them, this is how they look like. And the rule is that the 1 should always be somehow oriented so that it's positioned on the diagonal. Or if you wish to have a more mathematical formal way, it is positioned in the position II, where I stands for the indici 1, 1, 2, 2, 3, 3, and so on. Vectors. So a vector is now another special sort of matrix case where we will introduce a matrix of only one column and n rows, as we can see here by its notation, size of n by 1. We have special vectors that we work with, especially in our course, which are called the unit vectors, E of j, j being the position on which we will place the unit, the 1. All of the rest of the numbers in our vectors will therefore be 0. So this will indicate some sort of position in our vector that we have to be aware of. And we simply work exercises with this unit vector. There is not much of more of a theory regarding to it. But this is how it looks like, and this is how we represent them. Do you have questions so far? Before I move on to matrix operations, does everybody understand how the matrix looks like and the special case of the matrices? Okay, perfect. If the matrices are clear and we understand the types of matrices and how we work with them, then let's move on to operations. There are some basic operations of matrices that we're going to introduce. The first three, however, are the most important because we see them most frequently. Let's start with the equality of two matrices. So we call two matrices A and B equal if they have the same size and all of the elements on the same positions are equal. What does it mean that they are of the same size? So they have the same number of columns and the same number of rows, and the coefficients found in the same positions are also equal. We call a matrix transpose. So for example, denoted by the notation A of T, we call this matrix the transpose of matrix A when this matrix has the property that it has inversed the rows and the columns of our official matrix A. Maybe it sounds a little bit confusing. Let's move on back to our matrix A that we've seen in the first slide. And I would like you to pay special attention to the first row. So I'm going to read the first line. You see the numbers, the coefficients are A of 1, 1, A of 1, 2, A of 1, 3, and so on until A of 1, n, representing the fact that my coefficient A is found on the first line, position 1, 2, and n, according to the column on which we find it. How does it change when we transpose this matrix? Instead of reading this indici on a row, we're now going to read them on a line, as we see here in this matrix. So pay attention. Now I'm going to read the same coefficients as before, only we're not going to find them on the first line. We're going to find them on the first column. As you can see, A of 1, 1, A of 1, 2, A of 1, 3, and so on until A of 1, n. And instead on the row, we're going to find the coefficients we originally found on the first column. As you can see, A1, 1, A2, 1, A3, 1, and so on. So this is what a transpose is. Now, a special case of the transpose is the symmetric matrix. So the symmetry in matrices represents the fact that the matrix, so A, it will be equal to its transpose. This can only happen if our symmetric matrix is a square matrix. Does anybody know why symmetry happens only in the case where we have a square matrix? Does anybody want to tell me why? Thinking of symmetry as an equality between the matrices. So A has to be equal to A transpose. Yes, exactly, because the rows and the columns have to be equal in order for us to call two matrices equal. Therefore, in order for us to be calling a matrix symmetrical, it has to be a squared matrix, correct? The last operation we're going to tackle right now is the sum of two matrices. So the two matrices A and B should be of the same size, so the same number of rows and the same number of columns, and their summation will be denoted by the matrix A plus B, in which each element is the sum of the corresponding elements of A and B. As we can see here in our examples, this is the first matrix A denoted by the indici A1, 1, A1, 2, and so on, and the matrix B denoted by the same corresponding coefficients B1, 1, B1, 2, and so on. When we summate the two, we're going to add up all of the individual coefficients found on the same position into one new coefficient, which will be represented on that specific position in the newly found A plus B matrix. As we can see here, on the position 1, 1, we will have the summation of A1, 1 plus B1, 1. On the position A2, 2, we will find, on the position 2, 2, we will find the summation of A2, 2 plus B2 of 2. And that is it for summation of two matrices. And I think this is already a good enough time to start practicing with these matrix operations so that we can make sure we're all on the same size. So I will point you towards exercises 1.1 and 1.2 from your mathematics book. I also have the PDF here, so I will share everything on the screen so you can see, in case you don't have the book on hand. Okay, let's see. Okay, so right now you should be seeing my screen. If you can't, please let me know. However, let's start the exercise. I will also take my notes so I don't have to copy every time the matrices from the screen. Great, so we have to find the values A and B such that these two matrices are equal. So we have this matrix, I'm going to read the lines, 3, 4, A, 2, 5, 7, which should be equal to 3, B squared, 3, 2, 5, 7. What are we going to do? I'm going to move to the whiteboard. I'm going to clear my beautiful drawing, and I'm going to start writing down these matrices in the most convenient way I can. 3, 4, A. Oh, sorry. This should be A, and 2, 5, 7 should be equal to another matrix of 2 lines and 3 columns, 3, B squared, which I'm gonna write as B to the power of 2 like this, and 3, 2, 5, 7. We already see that the second row of each of these matrices is equal to one another. So we have already checked a couple of our elements together. So we know that the matrices are each 2 lines by 3 columns, which is true. These are 2 lines by 3 columns, 2 lines by 3 columns. So the first checkup point is checked. We see already the elements on the last line, so on the second line, are equal to one another. So 2 is equal to 2, 5 is equal to 5, 7 is equal to 7. So what we have to check is the first line, which is missing a couple elements. We know 3 is equal to 3. However, we don't know that 4 is equal to b squared. So I'm going to write ahead here. 4 is equal to b squared. This is one of the conditions that our matrices have to meet in order for us to call them equal. And the second condition is that a should be equal to 3. We already found the coefficient a is equal to 3, so that is done. What we now have to do is find out the values that b can take in order for this equation to be true. So we know that b squared should be equal to 4. What does this mean? It means that our b can be either 2 or negative 2. Either one of these values will give me the correct representation of b squared is equal to 4. Therefore, our options will be 3 and 2, or 3 and negative 2. So this would be the final answer of our exercise. And I hope everything is clear for everybody. In case it's not, please let me know so we can move on to the next exercise. Clear is the notation we should use for this. Is the notation we should use for the solution? It's not necessarily the notation you should use. This is the notation we use for pairs of solutions, or for solutions that come in pairs. However, in the exam, you may be asked what is A, what is B, and you will have, because I know the exam is on Canvas, so you will have special boxes for each of the answers. So A is equal to, B is equal to. But yes, generally, this is how we write down the solution for pairs of values. So it's an option. You can also write them down as A is equal to 3 and B is 2 or B is minus 2. It's your choice. Okay, if everything else is clear, let's move on to the next exercise. So this will be exercise 1.2, where I would like us to work a little bit with the symmetric of the matrix. So in exercise 1.2, we are given the matrix A in this form. What is this? This is a matrix of 2 lines by 2 columns. So this will be a squared matrix because it has the same number of rows and columns, right? So we are asked to determine A and B such that this matrix is symmetric. Okay. What does it mean that a matrix has to be symmetric? This is 1.2. So A is symmetric if A will be equal to A to the power of T, which is A transpose. Our matrix A looks like this. Will be a square matrix of, for A, 2B plus 2, 4, and 0. I think this is the correct, yes, that's correct. Great, so we know that A is symmetric if A is equal to A transpose. We have already checked that our matrix is squared, therefore we can work with the symmetrical point. What do we have to do now? We have to create the transpose of the matrix. So I'm going to go ahead and write the transpose of A. So A to the power of T will be equal to, does anybody want to help me out first? So we will read the row as a column and the columns as rows.
Is it A4 for the first one?
Yes. And then the row?
It's 4?
Yes.
Okay. And then I guess the bottom one is 2B plus 2 and 0.
Perfect. Yes, that's exactly correct. Thank you so much for helping me out. So Now that we have the two matrices, the A and the A transpose, we have to check for the equality. Therefore, we were going to do exactly what we had done before. We have to check that the numbers, the coefficients found on the same indici points are exactly the same. Let's check them visually first, and then we will write down the solutions. So we have to check that 4A is equal to 4A. Then we have to check 2B plus 2 is equal to 4. Then we have to check that 4 is equal to 2B plus 2. And then we have to check that 0 is equal to 0. So these are the equations that we're going to work with. I'm going to write them down. 4A has to be equal to 4A. 2B plus 2 has to be equal to 4. Then we have 4 is equal to 2B plus 2, so I'm not going to write it again because we're going to write exactly the same equation twice. It doesn't make sense. And then 0 is equal to 0. What do we know from these equations already? 0 is equal to 0. This is true. We have nothing against it. 4A is equal to 4A. What does this mean? It means that if we simplify by a 4, A should be equal to A. In other words, A can take any value. Because we are not given a restriction against it. We are just told that A has to be equal to A, therefore A can be of absolutely any value in the world. In regards to the second equation, 2B plus 2 has to be equal to 4. 2B plus 2 equal 4 means that 2B is equal to 4 minus 2. Therefore, B has to be equal to 1. For B, we therefore have a restriction. Then, how should our matrix look like? A can take absolutely any number. B has to be equal to 1. And for the rest of the elements, we don't care because they correspond with the transpose perfectly. So our final answer would be A can take any value and B should be equal to 1 for that matrix to be symmetric. And that's it. That's how we solve the exercise. I hope that was clear for everybody, but let me know if it wasn't, or if you need more time spent on this slide so you can maybe write them down or take a screenshot or however you feel comfortable. Okay, let's move on to the next part of our slides. So now we've understood a little bit about matrices. We've seen how they look like. We've seen how we work with them. We've understood a little bit about summation, transposition, and symmetry. Let's move on to other sorts of matrix operations, which we're going to find a little bit more complicated, but they're not. And also with which we're going to work with a lot more often. One of them is the scalar product of a matrix. So scalar product of a matrix A and the number C is denoted by C multiplied by A, and it is obtained by multiplying each element of the matrix with the number C. The number C, therefore, is a constant. It can be 1, it can be 0, it can be 3.7, it can be 0.84. It can be absolutely anything because it's a constant number, it's a scalar. So how do we do this operation? We simply write C multiplied by A, so the constant multiplied by the matrix. Therefore, the constant will be multiplied by each of the elements of the matrix, like we can see here in the example. If you guys wish, we can also see it live on the exercise. I thought we should work it on exercise 1 because it doesn't make sense to create a whole new exercise just for this matrix. And I'm going to use matrix A that we've seen here. And we're going to multiply it by 3, so we see what the deal is. So 3 multiplied by this matrix A will be this matrix, by the way, will be equal to what? This will be equal to 3 multiplied by our matrix, which is on the line 3, 4, and A, we established it's 3, 2, 5, 7. Therefore, 3A will be, let's see, 3 by 3 will be 9. There We move on to the next term. 3 by 4 will be 12. 3 by 3 will be 9 again. We finish the first row, we move on to the second row. 3 by 2 will be 6. 6. 3 by 5 will be 10. And 3 by 7 will be 21. I know my matrices don't look exactly eye-pleasing right now, guys, but when you write them down on a piece of paper, try to write them down, each of the coefficients, try to write them on top of one another so you don't confuse on which position they are located. I can't do that exactly on my computer, but for you, when you're working and practicing these exercises, it's really, really useful that they're really well aligned. I can't always do it on my computer, but I hope it's clear enough. 3 by 5 is 15. Yes, you're completely right. I forgot mathematics. I am so sorry. I got nervous for a second and look what happened. 3 by 5 is 15, of course. So this is how we multiply, how we do a scalar product, how we multiply matrices. I hope everything is clear for everybody so far. This wasn't a complicated operation as it is, but it's a really important one. So I hope it makes sense.
Maybe I have one quick question. So about the C, do they more often give like a number for C, so a value, or does it also occur very often that it's just a number that, like a letter that you have to multiply with the matrix?
I'm going to give you a confusing answer. It depends. So you can either be asked to calculate a scalar product between a constant and a matrix because they want you to multiply the matrix by something, or they can give you the final version of the matrix, so the resultant of the matrix, like for example, this version, and they can give you the original matrix and ask you what is the constant. You know, they can work around with that, they can play around with that. Or they can ask you what is the original matrix given the resultant and the constant.
Okay, yeah, okay, cool.
You're given something.
Thanks. No, it does help, so thank you.
No worries, absolutely. Any questions you guys might have, please go ahead and ask me. I feel more than happy speaking to you. So we've also done this. We can move on to the, I think is the last matrix operation we're going to show, which is the product of two matrices, or the product of a matrix and a vector. They're done exactly the same way, so I'm going to explain the one and we can work with the other. So the product of two matrices is a really interesting operation because it's one that requires a little bit more attention when creating the calculus. And I've included here two schemes of how the operation should be conducted. However, I would, looking over them and looking over my slides a little bit, I'm going to try to explain on this part of the picture, on the matrix multiplication, because I feel like it's going to be a little bit more well explained. So how do we multiply two matrices? We have here matrix 1 and matrix 2. We observe that they are they don't matter, that they shouldn't necessarily be of the same size. However, the number of columns in the first matrix must be equal to the number of rows in the second matrix. This is a rule we should always keep in mind. For square matrices, however, we know columns and rows are the same, so it doesn't matter that much. What we care about is the algorithm of how we have come up to these numbers in the resultant matrix. The unspoken rule of the multiplication is that each row of the first matrix will give out a new position for the next row in the resultant matrix. How does that go? It means however many rows we have in the original matrix, that's how many coefficients we're going to have on the first row of the resultant matrix. So if here I have 2 rows, therefore in the resultant matrix I will have 2 columns, let's say. Okay? That's how it works. Moreover, how do we actually do the multiplication? We are going to multiply and then summate indici. How does this work? We're going to take the first row of the first matrix with the first column of the second matrix. And we are going to multiply the first element of the first row by the first element of the first column. As you can see here, 3 by 1, which is equal to 3, plus the multiplication between the second element of the first row by the second element of the first column. So plus 4 by 3, which is 12. Therefore, we obtain 15. Once we have created the first operation, with the first row still working with the first row, we will move on to the second column of the second matrix. So we will move on and create the second element of the first row by multiplying 3 by 5, so first element by first element, so 3 by 5, 15, plus second element by second element, plus 4 by 7, 28, and that's how we obtain 43. Once the first row has been multiplied with all of the columns of the second matrix, we move on to the second row, and therefore we move on to the row 2, 1. Here we will go again, row multiplied by column, and so on, and that's how we obtain the new positions. So we have 2 by 1, 2, plus 1 by 3, 3. How do I obtain this again? First element by first element, plus second element by second element. The same thing is going to happen when we want to obtain the 17. We're going to multiply the first element of the second row, so 2, by first element of the second column, 5, so we get the 10, plus 1 multiplied by 7, and that's how we obtain the 17. I think these arrows over here are very suggestive and they are very, very helpful. And I also think something that helps me a lot, especially when I work with this matrix multiplication, I always do this. I always write down the result of the product plus the result of the second product and so on. So I never forget elements. I never write the matrix as the resultant matrix first, because it's a really, really easy way to make some mistakes or forget some elements, and then your resultant matrix will get all messed up. So this is a really good method. I don't know if my explanation was clear enough. Let me know if it wasn't. We're going to work an exercise and we're going to see the algorithm practiced anyways. But let me know, guys, if this solution was somewhat useful already. Okay, perfect. If it's clear, then let's move on to exercise 1.6, from which we will only do point A. I think it's a longer exercise, so one example will be more than enough. So we need 1.6. Where is exercise 1.6? Okay. In exercise 1.6, we are asked to determine, if possible, the product between A and B. So the product of A multiplied by B. For exercise A, we know it is possible because this is the reason why we're working with this specific exercise, to practice a little bit the product rule. However, can anybody tell me if we could at the same time multiply B by A? So not A by B, but B by A.
I think so, right? Because you need like the similar amount of rows as columns.
Sorry, can you say that again, because I couldn't hear you?
Yeah, of course. I said yes because we need the same amount of columns and rows, or like not the same amount of columns and rows, but like if we would multiply B by A, we would have 3 rows, and there would also be 3 columns in A.
Okay, so the rule is that the number of columns in the first has to be equal to the number of lines in the second. Okay.
Yeah.
So here we have 3 columns. Here we have 3 rows. Therefore, it works. If they are the other way around, we have 2 columns and 2 rows. So that's why it works. Okay. Okay, perfect. Let's work exercise 1.6. I hope you guys had a little bit of time to write it down. I also have it written down somewhere, but I'm going to write it again on the blackboard. Let's go ahead and write our matrices. A is equal to, and we have our 2 by 3 matrix which will be 1, 2, 1. And then we have 3, -1, and 6. So this is our first matrix. And then we have B is equal to, oh, this is a longer matrix, so it should be like this. B is equal to 3, 4, 0, 0, -2, and 1, 1. Okay, great. Now we are going to do the multiplication. So I'm just going to write A multiplied by B is equal to. I'm going to leave my matrices right here next to one another so I don't have to write them down again. However, I'm going to write down specifically and explicitly the operations that we're going to do. Okay, so I'm going to write my matrix a little bit longer so I have enough space, and we're going to start. So again, the rule is that I'm going to work with the first line of the first matrix and the first column of the second matrix first. How? By multiplying the corresponding terms by one another and summating the resultant products. So I'm going to have 1 multiplied by 3, which will be 3, plus 2 multiplied by 0, which will be 0, plus 1 multiplied by 1, which will be 1. And this will become my first element. What about my second element on the same row? It will be calculated by multiplying again the first row by the second column this time. So I'm going to go ahead and write 1 multiplied by 4, which is 4, plus 2 multiplied by -2, which is -4. So I'm going to write parentheses -4, plus 1 multiplied by 1, like that. Now that I finished multiplying the first row with all of the columns of the matrix B, I can move on to the second row. So now I'm going to go ahead and write 3 multiplied by 3, 9, plus -1 multiplied by 0, it's 0, plus 6 multiplied by 1, that is 6. I finished again with the first column. I move on to the second column. 3 multiplied by 4 is 12, plus -1 multiplied by -2 is negative with -2, plus 6 multiplied by 1, 6. This is my resultant matrix, and this will be equal to what do I obtain? 3 plus 0 plus 1, this is 4. 4 minus 4 plus 1 will be 1. 9 plus 0 plus 6 is 15. And 12 plus 2 plus 6 is 20. And this should be our resultant matrix. And this is how we obtain the elements. Was it clear enough, guys, the explanation and the way that we work with the matrix, with the product between two matrices? Yes, perfect. Great, then we can move on. Oh, it wasn't the last of matrix operations. We still have some properties that we need to discuss. And the reason why I feel like it's very important to go a little bit through these matrix operations properties is because I need to tell you something very, very sad about matrix operations. Although the summation, so the plus between matrices is a ambivalent equation, so writing A plus B will be equal to writing B plus A. The multiplication, however, is not. Unfortunately, when I multiply the matrix A by matrix B, so A multiplied by B, the result will be most of the times different from B multiplied by A. This happens because of the way the product rule is conducted, because of the way of this line by column multiplication. When you switch the matrices between them, the final result is not always the same. So please keep in mind that when you multiply matrices or vectors by one another, it matters greatly, greatly, greatly the order in which the product is conducted. So, therefore, we have these properties that we have to keep in mind. We have the properties for matrix vector product. Remember that the vector is a matrix with only one column and many, many rows. These will be our vectors x and y in this example. And C, just a constant, a number. The first property is that a matrix A multiplied by a summation of vectors, x plus y, can be rewritten as AX plus AY. Please pay attention to the fact that I did not, like the book, did not write them down as AX plus YA or, I don't know, XA plus AY. They are written in the exact order that they have appeared, A to the left and the vector to the right. Therefore, we have AX plus AY. This is the correct order of the multiplication. When we come up to the second property, the matrix A multiplied by a constant multiplied by a vector, here we can switch the place of the constant C because it's just a number that we're going to multiply our final result by, okay? So the constants are a different category in multiplication. However, the vector, again, the matrix vector multiplication, again, will be conducted in the order that it has appeared originally in the exercise. So A multiplied by C has remained A multiplied by, A multiplied by X has remained A multiplied by X and not the other way around. Same thing happens when we speak of matrix product, okay? So this is matrix vector. Remember, vector is a matrix with only one column. When we speak about the matrix product, the same rule applies, that the product rule is not transferable. So we always have to keep in mind the order in which our matrices have appeared. And I would point you to the first example. We have a summation of matrices in our parentheses, so A plus B, multiplied by matrix C. If we would like to open up the parentheses and do the multiplications first, we will multiply A by C plus B by C, which will be completely different if we had to multiply C by the parentheses. The order would have therefore been C by A plus C by B, and the result could be completely different. So always please keep in mind of this rule, which is illustrated through all of these examples as well. We can quickly go through them and check them out, look at them. But the most important thing to remember is that product is not transferable. So that's kind of what you want to remember. So if you know that X is equal to 3 and Y is equal to 2, can you say that A is equal to A multiplied by 5? If it could have been that if it were the case that X and Y are two numbers, two constants. However, here they are vectors. You can do the summation of the vectors first and then multiply A by the resultant vector. But what you have described here is an operation with a scalar, okay, so a constant. However, if you meant that can you add up the vectors together and then multiply A by the resultant vector, yes, definitely, you can do that. If you need to break them apart, however, this is the way that we do it, by the first property. Is that clear? Is that okay? Yeah? Okay, perfect. We have one more thing to explain before we finish officially with the first chapter, and we will officially take a break. So let's quickly go ahead and look at something called input-output models. There isn't much theory behind input-output models. It's just a type of application of the matrix. So I'm going to quickly go through this exercise with you guys. We're going to work it together, and I'm going to show you how exactly we work with it, how we do it. So let's read it all together. The investor in the previous example, which is an example from the book, has changed his investment policy. He would like to invest certain amounts in 3 cities, in Amsterdam, New York, and Frankfurt, in different industries. So he has a certain amount of money that he wants to invest in these 3 industries in 3 different cities. In Amsterdam, he invests his money in the following order: 30% in financial business, 20% in car industry, and 50% in computer markets. In New York, he invests 10% financial business, 40% car industry, and 50% computer markets. And in Frankfurt, he invests 20 in financial business, 50 car industry, and 30 computer markets. And we know exactly the amount of money he invests in each of the cities. He invests 5,000 in Amsterdam, 6,000 in New York, and 10,000 in Frankfurt. Our question is, how much money did he invest in each of the industries or specific markets? So this is what we have to calculate. And if you guys would like to read again the exercise, I'll give you a minute, or maybe take a picture of it or a screenshot, because I'm going to switch to the whiteboard to show you how we put together this information into a matrix. So I'll give you a couple more seconds before I do that. Okay, I hope everybody has had enough time. Now we're going to switch to the whiteboard and write this exercise down. So we are told that this investor had invested his money in a certain way in 3 cities, in 3 different industries. What do I already kind of get a hint of? That I'm going to create a matrix, evidently, with this information that I've been provided. However, it's really important the number of cities and the number of industries that I've been presented, because I know I have 3 different cities, and each one of these cities is divided into 3 industries in which he has invested his wealth. So my matrix A will therefore be a square matrix of 3 lines by 3 columns. Why? Because I have 3 cities, 3 industries. So I'm going to write it pretty largely so I have enough space. And I'm going to also write down here the corresponding city names, so you understand kind of what I'm going for. So the first column will become the Amsterdam column. The second column will become the New York column, and the third column will become the Frankfurt column. The order is not random at all. This is the order that the information has appeared in my text. So because they're giving me Amsterdam, New York, and Frankfurt in this order, it means that this is the order that I'm going to construct my information on, okay? So Amsterdam, New York, and Frankfurt, these are the 3 columns on which I'm going to write down the information. I also have 3 industries, and I also have to write down these 3 industries, this time on my lines. How do I write them down? The first industry that appears in the text is financial. The second industry that appears is car industry. And my third industry will be computer markets. So what is my matrix going to represent, therefore? The intersections between Amsterdam and financial, Amsterdam car industry, Amsterdam computer market, then New York and financial, New York and car industry, New York and computer market, and the same for Frankfurt. It will represent intersections of some percentages of this person investments in these certain cities, in these certain industries. So in the order that they have appeared in the text, I know that this investor has invested 30% of his wealth in Amsterdam in the financial business, has invested 20% of his wealth in the car industry, and the remaining 50% in the computer markets. For New York, however, we have different percentages. We have 0.1 in financial, we have 0.4 in car industry, and we have the remaining 0.5 in computer markets. And then our third investment, 0.2 in financial, 0.5 in car industry, and the remaining 0.3 in computer market. And this is how our matrix A has appeared. These are the corresponding percentages as written by the text. We also have another matrix, which we can call, however you guys want to call it, we'll call it, I don't know, M from money invested, which will represent the amount of money that he has invested in each one of the cities. And we know this is a matrix of only 1 column and 3 lines because he has invested in 3 different cities, and that's it. And the respective amounts are 5,000 euros invested in Amsterdam, 6,000 euros invested in New York, and 10,000 euros invested in Frankfurt. What the exercise is asking us to do is to calculate how much money has been invested in each of the industries. So how much money has been put together in financial, how much money has been put together in car, and how much money has been put together in computer market. So I'm going to have to multiply A by the matrix M, this matrix right here, to obtain the matrix AM. And how do I do this? I'm going to literally do the multiplication like we have done it before using the product rule. I'm going to write it like bigger like this so I have enough time for my calculations. And I'm going to go ahead with the product rule. How do I do that? By multiplying the rows from my column A by each of the, from my matrix A by each of the column in my matrix M. I have only one column, so my job is going to be really easy. So what do? I have to go ahead and multiply 0.3 by the first number, so 0.3 by 5,000, 0.3 multiplied by 5,000 plus 0.1 multiplied by 6,000 plus 0.2 multiplied by 10,000. Like that. Yes. And this will become my first element of my newly found matrix. I go ahead and I start writing down the second element because I have finished the first row and the only column. I move on to the second row, which will be described by the equation. 0.2, so the first element multiplied by first element, 5,000, plus 0.4 multiplied by 6,000, plus 0.5 multiplied by 10,000. Like that. And again, I finished all the rows, all the columns. Oh, sorry, I finished the row multiplication with all of the columns. I can move on to the last row, which will be described by 0.5 multiplied by first element 5,000 plus 0.5 multiplied by the second element, so 6,000, plus 0.3 multiplied by 0.3 multiplied by 10,000. Now I would have to go ahead and do some calculations, which I'm not going to go ahead and write all over again because I've done them already and it takes some time. So I'm just going to write the final answer for you guys. We should obtain, by doing this calculus, 4,100 euros invested in the financial industry, then 8,400 euros invested in the car industry, and 8,500 euros invested in the computer markets industry. And this should be our final answer, the matrix 4100, 8400, 8500. Yes, it's 050503. Why did I write them? Wait, let me look. 05. Yes. Is everything clear to everybody? The way that I've calculated, conducted the product rule? This is on the rows. Can you also put the cities on the rows and the car industries on the columns and still obtain the right answer? Only if what you're literally saying is asking if it matters if the matrix is A or A transpose. It wouldn't have mattered if A would be symmetrical. However, A is not symmetrical. If you switch the order of the rows and the columns, I think you will obtain a completely different answer because A is not symmetrical to A transpose. So the way that you write your information is important. How do you know what to put on the columns? Great question. When we deal with input-output exercises, we always deal with percentages of investment, percentages of ownership, and so on. The percentages are written on columns because put together, a column should be equal to 1 in the input-output examples, okay? So not generally when we're doing matrices, but in the input-output models, a column should be equal to 1 in the end, corresponding to 100%. So when you're given information about investments in cities, and you know that in a certain city has been made an investment in 3 or 4 or 5 different markets, it means that the investments are going to be put on a row, and the markets are going to be placed on the investment is going to be written as a column, and the corresponding markets on the corresponding lines. Because again, a column should be equal to 100% in total when we're dealing with input-output models, okay? So these represent percentages, right? You can see that when you add up the percentages on lines, you don't get 100%, you get either less or more, and that is because this is completely different information. I don't want to lose you too much with this explanation because it's a little bit more complicated than this, but what you should generally get from this is that a column should be what you're looking for to become 100% because you're dealing with percentages. Was that a little bit more clear? Okay. Okay, great. If there are no more questions about this exercise or this chapter 1 in general, we are going to take a short break. I don't know, what do you guys think? Maybe 5 minutes should be enough because this wasn't a super complicated chapter. What do you guys think? Could this be an exam question? Yes, definitely. Could be an exam question. It's also structured in the way that the exam is structured, so with a lot of text from which you have to deduct information. So the input-output model, yes, definitely. Everything we're discussing is kind of very, very much related to how the exam is going to look. I've tried to pick exercises that I know are very similar to what you could obtain. But the input-output model, yes, especially, because it's an application. And I've seen the professor is really keen on applications more than theory. Are there any other questions before we move on to the break? No? Okay. If not, we will take a 5-minute break. So everybody be back at 10 and 6 minutes, and we will discuss chapter 2. In the meantime, I'm not going to go anywhere. I'm probably just going to go grab a cup of coffee. So if you have questions, we can discuss. If not, enjoy your break, and we'll see you guys in just a little bit.
Bianca? Wait, let me. Hi.
Hi.
So I have a question in regards to the question of evil. Can't we like switch the places in like the matrix? Like he said, like put the cities, as rows and the industries as columns. If we also do the M matrix so that it is 3 by 1, I think it would work. Like if it's like not a vector, but it's like.
Oh, so it's a line.
Yeah. Because if you multiply, I think you can get still the result.
I don't think we can do that just because, so the number of columns in the first matrix is 3. It has to be equal to the number of lines in the second matrix. So if we transpose the second matrix, which is 3 by 1, it will become 1 by 3. So the number of rows will be 1.
Yeah, but like, isn't it? Yeah.
Because the matrix is a 5,000, 6,000, 10,000, one on top of another. So that means it's 3 rows, although it's 1 column. If we transpose that, it is possible to transpose it, of course, but we cannot do the multiplication because the rule doesn't allow us, because we don't have enough lines in the second column.
Okay. I was just asking. Thank you.
Of course, you can ask me absolutely anything, guys. This is why I'm here. Okay. So our break is also officially done. I'm sorry, guys, to disappoint you, because I know it's so always really sad when people hear the break is over. However, we have to get back to work. We have a lot of stuff to do in chapter 2. Very beautiful things. That's how I like it. Never hard. Mathematics is never hard. Mathematics is just beautiful. One more second before we begin. And we'll speak about systems of linear equations. Great. So, systems of linear equations. How do we switch from matrix to systems of linear equations, you may ask? Well, let's think a little bit about what we have learned, what we have done, and how it connects. So we have explained already that the matrix is a rectangular scheme of numbers that describes what I told you initially are positions or numbers in certain positions because they are indicated by indici. They are actually coefficients. And these coefficients describe a system of equations. That's why we first learn matrices and we introduce them and we learn how to work with them. So then we can now actually attribute the coefficients of the matrix into a system of equations. But first, what is a system? System of linear equations is a collection of one or more equations that involve the same set of variables. Why linear? Because they will always describe a line on a graph. And they will always be, the variables in the system, which are the variables x, will be to the power of 1 maximum, okay? They can also be 0, so we can have no variable of such, but they mostly are to the power of 1. A system looks generally like this form. So it contains lines of equations that are described in terms of the coefficients of a matrix and the corresponding variables. And they are in the end equal to a number, which we will here indicate as B. I've written here down the system, a little bit of an explanation of what these numbers indicate, in case you have forgotten, that any indici any number or any coefficient A of the indici I and J, so any of these A's, are the coefficients or the positions taken from the matrix. And our x's in this system represent the variables. Okay, I told you before, the system describes the equations which are attributed to the matrix A, which contains the coefficients used in our system. Now, what is the mathematical representation of such a system, including the matrix notation? Matrix A will be multiplied by the variable vector x in order to obtain another vector, which we will call the known vector of the system, indicated by the letter B. Notation is A multiplied by X is equal to B, and graphically represented, it looks like this. The matrix A, which is our m by n matrix, multiplied by a variable vector X. So when I call it variable vector, it means that it contains all of the variables from x1 until xn that we will find in our system, will be equal to the known vector of the system B, which contains these answers of my system. So the answers of my system will be contained into this variable vector B. This is the notation. This is the, I would call it graphical representation. And that is basically a system. We're not actually practicing right now, so I don't want you to think that we're starting to solve systems. However, I would like to show you how they look like and how we transpose from system to matrix and from matrix to system, which I think is important to already have a little bit of an idea about, okay? So I will point you to exercise 2.1 from the book, which I also have, oh, I forgot to look for the exercise during the break because I was busy getting coffee. This is what happens. Where is exercise 2.1, 2.1. Ah, it's here. Great. Okay. We have exercise 2.1. We have here represented in exercises A and B two systems of equations, and we are asked to determine the matrix vector notation of the following systems of equations. I would have explained in the slide what the matrix vector notation is. However, I think it's much more useful if I explain it while you also see what it means. I think it's better to also have the visual at the same time. We're not going to work both the exercises together. I'm going to work the exercise A by myself with you on Zoom, and I would like to ask you guys to work exercise B by yourselves and let me know what the final result of the matrix vector notation you obtained, because I would like to see that you understood. So I'm going to write down first the first exercise. I'm going to write it down here for all of us. A system will be held together by this weird parentheses, which will always be written to the left of the system. And in this space that the parentheses allows us, we will write down all the equations of the system. So we have 2x1 plus 3x2 plus x3 is equal to 4. We have x1 plus nothing, so plus 0, plus x3 is equal to 1, and nothing, so 0, plus x2 plus x3 is equal to 2. This is my system of equations. You probably have noticed that instead of leaving a blank space where the exercise has left a blank space, I have written down a 0. This is not random at all. This is to help you visualize a little better what we have to introduce into our matrix and why. I've told you that a system of linear equations is described by the coefficients of a adjoining matrix. So from this system, I can deduct the coefficients of my matrix A that is corresponding to these equations, or from the matrix A, I can deduct the coefficients of my system described by these equations. The operations are go both ways. Let's go ahead and write down what this matrix A would look like, right? Because I've told you that it describes the coefficients of the system, so let's see how it looks like. In order to understand or to compute A from this system of equations, we have to take into account the number that is multiplied by each of the x variables in the order that they have appeared. Only the numbers multiplied by the x variable, however. So I'm going to write down the first row of my matrix as the coefficients attributed to x1, x2, and x3 of my first line of my first equation. So 2 multiplied by x1, which one is the coefficient? 2, because x1 is the variable. So this is the first element of my matrix. 3 multiplied by x2, the coefficient is 3. 1 multiplied by x3, because x3 by itself means that it has been multiplied by 1, we say. So the coefficient is 1. That's excellent. I finished the first row. I'll move on to the second one. x1. Because it has no coefficient, it means that it was multiplied by 1. Then nothing or 0, meaning that my x2 variable has been multiplied by the coefficient 0, therefore it has disappeared. Therefore, in my matrix, I will write down 0. And the last term, 1, because 1 multiplied by x3 is equal to x3. I finish the second row, I move on to the third row. Again, nothing for the first position, meaning that the coefficient is equal to 0. Then I have coefficients 1 and 1. 1, 1. What is this? What have I deducted? I have deducted from my system of linear equations my corresponding matrix of coefficients. Great. I also called this matrix A. However, it doesn't have to have a name necessarily, but I like to call it A. And this is the matrix of my coefficients. If I would like to write the matrix vector notation, so what the exercise is actually asking me to do, the matrix vector notation, it means that it wants me to write down the extended matrix of coefficients. The extended matrix of coefficients is literally represented by the matrix of coefficients A, to which I add one more column. So instead of being a 3 by 3, it will be a 3 by 4 matrix, which will also contain the values of the system. So instead of writing A, I will write extended A, which will be the extended matrix of coefficients, like I told you, which will be a 3 by 4 matrix, because it will contain the same number as my original coefficients, plus a new row, a new column, on which I will have these values. I'm going to write it down like this, so you understand what I've put in here. And I'll show you how we write it down. I'm first going to write down my normal matrix. So 2, 3, 1, 1, 0, 1, 0, 1, 1. And now the last column of my matrix will be the values of my system. 4, 1, 2. And this is the matrix vector notation of a linear system of equations. So it's the extended matrix of coefficients, which includes the coefficients of the system, to which we add one more column with only the values of the system. And this is how we solve exercise 2.1. Was this well explained? Did you understand, guys? Yeah? Okay, perfect. Then you have to do as homework, if you will, point B for when you want to practice, because we have to move on to the next set of exercises, which will include the solutions of a system of linear equations, my favorite part of this chapter. What is a solution of a system of linear equations? A solution is represented by the vector of variables x that satisfies the equations of the system. What does that mean? It means that in my system of linear equations, coefficients get a value, so they are actual numbers. The b's also get a value because they are also actual numbers. And what I have to find out is the corresponding variables x that put together give me correct representations of these equations all together at once. So in a system, all of these equations have to be true at the same time. So for the exact same values of x. That's what it means. Therefore, when we look for a solution, we look for the vector x, so this vector right here, which satisfies at the same time all of these equations in my system. there are three possible cases of solutions. So a system can either have one solution, so only one vector that can satisfy my system. It can have infinitely many solutions, so it means that my vector can have infinitely many x's that are all equally possible to happen in my system, or no solution, meaning that the system has something incoherent that we cannot solve, therefore it has no solution. Therefore, we will call a system consistent. If it has one or infinitely many solutions. So generally, if it has solutions, it's called consistent. And if it does not have solutions, it's called inconsistent. Moreover, we will call a system homogeneous if its vectors of known elements B, so the equality of my system, is equal to the null vector. Therefore, all of the B elements are equal to 0. We're giving a better look at our initial system of equations. This system would have been homogeneous if all of these equation lines would have been equal to 0, 0, 0, 0. So this B vector would have been equal to 0. So these are the possibilities of solutions for a system of linear equations. How do we find these solutions? So we will use something called the row reduction procedure. This is a mathematical technique that allows us to find the solutions by working with the system in a, I would call it, ordered way. So there is actually a certain algorithm that we can apply all the time in order to discover x1, x2, and x3, x4, and so on. So all of the x's for my solution vector. What does this row reduction procedure entail? So it allows us to interchange equations. It allows us to multiply the equations by non-zero numbers. I hope this is self-explanatory because we can never divide anything by 0, or we cannot multiplicate anything by 0 in equations because our equations would disappear. Or we can add or subtract equations from one another. The row reduction procedure steps. This is very easy to remember, especially when we start exercising with them, and you will see just in a minute in an exercise. We generally follow these steps because I've noticed it myself. It just makes sense. Every time I cannot get a system together, I cannot find a solution of a system, I remember that, oh, okay, maybe I did not eliminate the variables in the correct way according to the row reduction procedure. And once I do that, I always get the system somehow. So although it may seem weird or very narrow-minded to always eliminate in this order, trust me that it works because probably the system has also been created in a way that the row reduction procedure works on it. So that's why we teach these steps. How do we do it? We will try to eliminate the variable x1 from all of the equations except the first one. So kind of remember that you eliminate variables from all of the rows. This is going to sound weird. You know, the variables have an indice. So x1 has an indice 1. First row has also an indice. It's called row 1. Row 1 will be the row on which we will find variable x1. Row 2 will be the variable on which we will find the variable x2. Row 3 will be the row on which we will find the variable x3, and so on. Why? Because the rows are coordinated with their specific indici. So when we're creating the row reduction procedure, we have to eliminate the variables x1, x2, and x3 from the rows that do not contain their indici. Therefore, x1 found on row 1 will be eliminated for row 2 and row 3, row 4, and so on. x2 will be eliminated from row 1, row 3, row 4, and so on, except for row 2. The same for x3, and it goes on like that until you've finished reducing all of your variables. This is the procedure. I know it probably sounds a little too weird, too theoretical, because I've explained it just like that. So I will work now with you guys an exercise. Actually, 2 exercises we will work together. Exercises 2.7 and 2.8, so we can get a little bit of a better idea of how we work with these matrices. And afterwards, I will let you 10-15 minutes to work exercise 2.9 by yourselves, and then we will move on. So we will first go on to exercise 2.7, and then we will move on with the lesson. So let's go. From the book, exercise 2.7. Many steps, many equations, 2.6, very, very close, 2.7. So we'll work this exercise as a warm-up first, because I would like to practice a little bit the product rule as well, and then we'll move on to 2.8, which is an actual system of equations. So we have to take a matrix 2 by 2, which is called A, that satisfies the following equations. So satisfies the following equations means that it exists. So a matrix of 2 by 2 exists, so that these equations are true. So matrix A multiplied by the vector 1, 0 is equal to vector 1, 3. Matrix A multiplied by vector 0, 1 is equal to vector A2, A being an unknown we have to find out. Matrix A multiplied by vector 4, 2 is equal to 6, 16, and we are asked to determine this coefficient A of this vector. This is what we have to do. I'll give you guys another few seconds to copy down the exercise if you need so, and then I will move on to the whiteboard. We will work this exercise together. Okay. I hope you had enough time. I'm also going to write it down on the whiteboard, but just in case. So we are told that a matrix of 2 by 2 exists such that those conditions of those equations are met. And because I don't know how my matrix of 2 by 2 looks like, I am going to take a matrix A with some random variables inside. And I'm going to call these variables, they literally doesn't matter how you call them, because we are going to find these numbers anyway. So I'm going to call them B, C, D, and E. I didn't start from A, which I know is weird, because we have to find out the coefficient A of one of the vectors. So I didn't want it to be confusing. So I decided to start my matrix notation with B, C, D, E. What are these? These are the coefficients of my matrix, and we have to find them. What do I know? I know that by multiplicating A with the matrix, with the vector, 1, 0, so 1, 0, I obtain the matrix, the vector 1, 3, 1, 3. I know this. If I know it, it means I can use the product of this multiplication in order to already gain some information into what these coefficients are. So I'm going to go ahead and write down the product between B, C, D, E and the vector 1, 0. So let's do it all together. According to the product rule, I have to multiply the first row of my matrix with the first column of my second matrix. So B multiplied by 1 will be B, plus C multiplied by 0, that is 0. Finish the first line. I move on and go ahead to the second line. B multiplied by 1 is equal to D, plus E multiplied by 0 will be 0. What have I obtained? I've obtained a vector matrix, which will be described by my coefficients B and D. And this vector matrix will be equal to the vector 1, 3. What have I learned in the first chapter? That two matrices are equal when they are both of the same size, which is true. They are both of 2 lines, 1 column, and the coefficients on the same positions are also equal. Therefore, what am I going to say? In order for these two vectors to be equal, B has to be equal to 1 and D has to be equal to 3. I've already found 2 of my coefficients from my original A matrix, which is great. I can go ahead and rewrite my matrix A as it's going to be 1C and then 3E. 3E. With this matrix now, because I found out the coefficients, so of course I can use them, I'm going to go ahead into the second equation that the exercise has given me. The second equation describes the matrix A, which is our matrix, this one. I'm going to write 1C, 3E. So I can multiply this matrix by the next vector matrix, which is A2. A2. I'm going to go ahead again and write down the resultant of this product. And what am I going to obtain? Again, doing the product rule. 1 multiplied by A, so that is A, plus C multiplied by 2, that is 2C. Finish the first row with the first column. I move on to the second row. 3 multiplied by A plus 2E. Oh, sorry guys, I have made a mistake. And none of you corrected me. I'm just kidding. I had made a mistake because A2 was the answer. What we had to multiply this matrix with was 0, 1. I didn't notice it, and that's my mistake. Let me try to correct these if I can. Can undo. That's much better. So I'm sorry, because the exercise had originally told us that A multiplied by the vector 0, 1 is equal to A2. So the matrix A multiplied by the vector 0, 1 will be equal to the vector matrix A2. A and 2, like that. Now we can solve the exercise. I'm really sorry. So what we obtain instead? We will obtain this matrix described by the equations. 1 multiplied by 0, that is 0, plus C multiplied by 1, that is C. And the second element will be 3 multiplied by 0, that is 0, plus E multiplied by 1, which is E, which will be equal to the vector C, E. And this vector should be equal to A2, because that's what the exercise told us, that the result of the product should be equal to the vector A2. Again, what does it mean for us? When we have to do the equality between two vectors, it means that C should be equal to A and E is equal to 2. I've already found the coefficient for E. Therefore, in my original matrix A, I can go ahead and replace E with 2. And I've already had 3 of my coefficients. All I have to do is find C, which is equal to my unknown coefficient A, in order to fully solve the exercise. So the next and last multiplication that we're going to have to do will be between matrix A, which will now be written as 1 C, 3, 2, because these are the results of the coefficients that we found already, multiplied by the vector 4, 2, has to be equal to the matrix, vector matrix 6, 16. What do we know? We know that 1 multiplied by 4 is 4, plus C multiplied by 2, this is 2C. And then we have 3 multiplied by 4, which is 12, plus 2 multiplied by 2, which is 4, has to be equal to the vector, I'm going to write it here like this, 6, 16. Again, what do I know about my matrices or vectors when they have to be equal? Same size, same number of lines, same number of columns, that all matches. It means that all that's left are the elements to be checked. It means that 4 plus 2c should be equal to 6, and 16 should be equal to 16. 16 is equal to 16, that is correct. It means that the only equation that still has to match is 4 plus 2c is equal to 6, which means that c should be equal to 1. If c is equal to 1, from before we know that c is equal to our unknown element a, it means that a is also equal to 1, which is what we should have found out from the beginning. This is what the exercises asked us to find out the unknown element a, so that this 2 by 2 matrix exists and all of these equations match. Therefore, this is how we find a. And this has been a really interesting exercise. We get to practice a lot with the product rule. Do you guys understand what we've done? Does this make sense? Is it easy? Is it okay? Do we know how to work with the product rule now? If there's no questions, then I will move on to exercise 2.8, which is the exactly next exercise in the book. And now we will work with a system, and we will have to apply the row reduction procedure. So exercise 2.8 reads, determine a solution of the following system of linear equations. And they're giving us the system. We'll read it all together. x1 plus 2x2 plus x3 should be equal to 8. Minus x1 plus 3x2 plus 4x3 is equal to 7. 2x1 minus x2 minus x3 is equal to 7. Determine a solution means that we have to find out the vector x1, x2, x3 that can be perfectly put into my system. So all of these equations at the same time are true. So this summation is equal to 8, this summation is equal to 7, and this subtraction is equal to 7. Okay, this is what we have to do. Again, a couple more minutes for you to copy down the exercise. We're also going to write it on the whiteboard. I'm going to explicitly write what we do. And afterwards, I'm going to give you, like I said, 10 to 15 minutes, but I think 10 will be okay, for exercise 2.9. So you solve a system yourselves, and we just check the final answer together. And in case you miss anything on the way, don't worry. I have some exercise. I have all of these exercises written down on some pieces of paper that I'm going to share with you after the class. So in case you did not get to copy down some notes, we also have that covered. Great. Let's move on to exercise 2.8. Exercise 2.8 tells us we have a system of linear equations described by the following equations. x1 plus 2x2 plus x3 is equal to 8. We have negative x1 plus 3x2 plus 4x3 is equal to 7, and 2x1 minus x2 minus x3 is equal to 7. I hope I copied down correctly. If I didn't, let me know. I'm just trying to check. x1, 2x2, x3 minus x1 plus 3x2 is 4x3, x1 minus 8, 7, 7. Okay, so the system is written down correctly. And now we're going to start solving it. I told you that what we're going to use is called the row reduction procedure. This is just a fancy name. What we're literally going to do is work with the equations with one another by adding or subtracting equations from one another, by multiplicating equations with numbers, and so on, in order to come up to the form x1 is equal to, x2 is equal to, x3 is equal to. So that is our final thought. That is what we should always keep in mind. I've also told you that the procedure, the correct procedure to solve such systems are to first eliminate each of the x's from the lines that do not correspond to its indici in their order. So first we eliminate x1, then we eliminate x2, then we eliminate x3, as much as we can, until we get to the point where we can't work with the procedure anymore and we just like do random things. But that's not really going to happen because we don't work with exercises that complicated. But if it happens, just know that it's completely fine. Sometimes that's just life. So we'll move on and start the exercise. The first procedure I would do, because I need to find a way to get rid of x1 from here and from here. So what I first need to do is get rid of these two variables. If I look a little around through my numbers, I see that I could make a connection between rows 1 and 2 and row 3. Why? Here I have 2x1, and here I have 1x1 and 1x1. I can make use of these two rows in order to reduct completely my x1 here, basically make it disappear into a 0. So my idea is that I'm going to work on row 3. So row 3 will be the one that's going to be changed. And what I'm going to do is subtract the first row from it, so minus R1. Why am I going to subtract row 1? Because I need to do 2x1 minus 1x1 to get to a smaller number of x's, so I'm going to have only 1x1 left in the end. And I would also like to make use of row 2, because here I have a negative x1, in order to fully get rid of this element right here. So from the third row, I'm going to subtract the first one, and I'm going to add the second row. Why am I going to add it and not subtract it? Because my coefficient x1 here has a negative sign in front of it, which means that when I add it, the actual operation that happens between the x's is a subtraction. Otherwise, if I were to write down minus R2, I would have had a minus x1, which would have ended up in me adding the number instead of subtracting it, okay? Great. Again, when we're doing row operations of such sorts, we are only working on the first row represented on my very big arrow. So lines 1 and 2 will be left untouched. The only thing that's going to change is row 3. How? Let's see. I'm first going to write the first two rows down fully. x1 plus 2x2 plus x3 is equal to 8. Minus x1 plus 3x2 plus 4x3 is equal to 7. And now I'm going to write down the row 3 with the changes that I have made. And I'm going to ask you to pay very, very close attention to what I'm going to explain, because it's going to be probably a lot of information. We're first focusing on x1. 2x1 minus row 1. So minus x1 will be x1. Plus negative x1 will become 0. So the operations that I do is 2x1 minus x1, which will remain 0. Plus, now that I finished with x1, I move on to x2. Minus x2 has to be further subtracted with negative 2x2. So minus x2 minus 2x2 will be minus 3x2 plus 3x2. I'll get another 0. It's great. I've already reduced 2 of my elements from my third row, which is amazing. We want to reduce as many as possible. Plus the last element, minus x3. Minus x3 will be minus 2x3 plus 4x3. So minus 2x3 plus 4x3 will be plus 2x3 equal to 7 minus 8 is minus 1 plus 7 is equal to 6. And that is the first step in our row reduction. I've reduced x1, and incidentally, I've also reduced x2. From the third row, I've only left the third row standing with its correct variable on it, which is x3. Now I can go ahead and do more operations on my third row because I would like to leave it in only x3, so I'd like to get rid of this 2. Therefore, I'm going to write again the first 2 rows untouched. 2x2 plus x3 is equal to 8 minus x1 plus 3x2 plus 4x3 is equal to 7. And the last row, 0 plus 0 plus x3 is equal to 6 divided by 2, 3. I've already found out the third x of my x vector solution. I know x3 should be equal to 3. However, I'm not going to change and replace this value in my system because I still have some x's to work with here, and it might be more helpful if I see it in an x3 form rather than its actual value. So we're just going to leave it intact. We're going to leave it as it is, and we're going to reduce x3 as we go. But this was kind of the first step. Looking at my system now, I know there is more things I can do in order to reduce now x1 from the second row, because I still have an x to reduce. So I know I have to work on the second row. So I'm going to write row 2. And I'm going to have to do something to row 2 in order to get rid of this negative x1, because I need to get rid of all of the x1s first. What is the only thing that I can do? I can only do operations with the first row because it's the only one that still contains x1. How do I get rid of minus x1? By adding 1x1. So I'm going to add to the second row the first one. So the operation I'm going to do is row 2 plus row 1. The result of my equation will be that x1 does not change, x2 will change, and x3 does not change. So we go ahead and write x1 doesn't change because we didn't do anything to it. X1 is, row 1 is x1 plus 2x2 plus x3 is equal to 8. Second row changes. How? Minus x1 plus x1 will become a 0 plus 3x2 plus 2x2 will become 5x2 plus 4x3 plus x3 will become 5x3 equal to 7 plus 8, 15. And then our third row, 0 plus 0 plus x3 equal to 3. This is a great example to see as a first system, because we already see how the zeros should be starting to form so that we can get rid of all of the variables that we don't need. What is the next thing that we should do? In my opinion, we should simplify this row, so row 2, by a 5, because we have here 5x2, 5x3, and 15. They are all divisible by 5. Therefore, we can eliminate it and leave our equation in a simpler form. So I'm going to write it down here, the new system. So again, I'm not going to change anything except for the fact that I'm going to divide the second row by 5. So x1 plus 2x2 plus x3 is equal to 8. Then I have 0 plus 0 plus, 0 plus x2 plus x3 is equal to 15 divided by 5 is 3. And then I have 0 plus 0 plus x3 is equal to 3. Now we have two possibilities. We can either be great students and go ahead with the row reduction procedure and eliminate from row 2 row 3. So we would do row 2 minus row 3 in order to get rid of x3. By getting rid of x3, we will come up to the conclusion that x2 will be equal to 3 minus 3, that is 0. Or we can do the easier way, which I'm going to do that now, and creating a smaller parenthesis between these two equations, so kind of like on the side. I know x3 is equal to 3, and I know x2 plus 3 is equal to 3. What does this tell me about my x2? That x2 will be equal to 0. Because I know x2 is equal to 0 and x3 is equal to 3, I will already go ahead into my first equation and simply write down what x1 would become. So I know x1 will be, the first row will be x1 plus 2 times 0 plus 3 equal to 8. What does this mean? It means that my x1 will become 8 minus 3 minus 0, 5. And I found out all of the coefficients of my x solution vector. I know x1 is equal to 5, x2 is equal to 0, x3 is equal to 3. And if we were to go ahead and input these numbers, 5, 0, 3, into the system, we would actually obtain the numbers 8, 7, 7 for the equations. However, we're not done. We have to write down the solution in a formal way, right? So the formal way of writing down our solution x is equal to vector. We have x1, x2, oh, what did I do? x1, x2, x3, because this is our solution vector x, will be equal to, and now writing down our actual solutions in the order of their x's, so 5, 0, and 3. And this is how we write down our final solution, 5, 0, 3. And this is how we solve the exercise. And this is basically the row reduction procedure in a gist. The reason why I've told you guys that we're not going to be good students and we're going to work a little on the side of these equations is because theoretically, you are supposed to keep on reducing these lines until you get x1 in this position. So you get x1 here, x2 here, and x3 here, and all of these other coefficients are equal to 0. However, in the exam, you're not asked to do this. You're asked to find the final solution. So if at some point you get to some equation that you can just start obtaining your x's one from another, you can stop the row reduction, you can write directly your solution because nothing changes, absolutely nothing changes. The only thing that is changed is the time that you spend on the exercise. But yes, this is how we work with this solution. Okay, so Simon has asked us, could R3 minus 2R1 also be possible? I assume in the beginning, because I remember I saw the chat popping up earlier. Yes, it could also be possible. However, me doing the exercise from before, I knew that this would have been an easier way, so doing R3 minus R1 plus R2, because I know it would also reduce my X2. So that's why I chose to do it. But it's also a matter of practice and exercises and tryouts. But yes, it's also possible. As long as you reduce the elements in the order that you're supposed to reduce them, everything that you'll obtain is correct. How did you find this exercise, guys? Did you find it doable? Was it okay? Yes, so wait, Dewey asks us, can you explain the difference in computing one solution, no solution, infinitely many solutions? So this is a clear example of one solution. It's one solution because each one of the x's has only one possibility. So x1 can only be 5, x2 can only be 0, and x3 can only be 3. So this is why it's one solution, because each one of these can only be one variable in this context. Infinitely many solutions would have been, for example, us coming up to the conclusion that one of these x's can be any number, absolutely any number. So x1 could have been the entire the entire natural system of numbers, for example. That would have been an example of infinitely many solutions. No solutions would have implied that our system is inconsistent and something does not match. For example, we would have come up with the conclusion that 0 is equal to -3 at some point through equations, or I don't know, something that tells you, okay, this is impossible. That's how you come up with no solutions. We will have some exercises with them and we will see them a little bit more practically explained. But generally, this is the method. You kind of understand whether you have solutions or not through row reduction and through these exercises. Is this a little bit more clear now? Great. All right. As I've promised you, I'm going to give you, I think 10 minutes will be sufficient because without my explanations and stuff, I think the exercises should shouldn't take no longer than 10 minutes. I'm going to ask you to do exercise 2.9 on your own. And when you're done, I would like you to write the answer in the chat in this form. So like that, with a parenthesis and x1, x2, x3. Because I would like to see that you understood how to work with row reduction on your own, in your own rhythm, with the operations that you feel most comfortable with. It's a system of equations that is doable and has one solution, so don't worry, we're not going too in-depth right now. And you will have 10 minutes for it starting now. So I'll be back to check on you at 11 and 7 minutes. And I'm going to leave the screen shared exactly like this so you guys can have the exercise for yourselves. Okay? I'll see you in 10 minutes.